Please put your hands together and join me in welcoming Ben and Prashant to the stage here at ShmooCon.
Hey everyone, thanks for being here. I know there's some good competition here in the sense that there are 2 other nice talks going on, and we're sad to be missing some of them as well, so I really appreciate you all being here. So I'm Prashant. I'm a researcher at North Industries, and I'm broadly interested in network protocols and file format security, and I used to be a PhD student at Dartmouth. And
I'm Ben. I'm a PhD student at Dartmouth, and I have 2 wonderful, beautiful cats, David and Dale, who will be featured throughout the presentation.
Yeah, we kind of like the symmetry of this particular slide. The reason why we actually went down this whole rabbit hole of exploring HTTP 1.1 implementations was that we got some funding to actually explore parser differentials in HTTP implementations, and in like a little over a month since we started this work, we reported our first vulnerability, and since then there were tons of them. And then in the middle of November, the project officially ended, and then here we are. So I'm sure that HTTP as a term, at least a lot of you would have heard of. It's essentially just a request response protocol where you have a browser or a client that crafts a request and then sends it to a server, and the server then responds back with a certain body. And an HTTP request essentially has 3 parts. There are 3 portions to it. The first is the request line, where you have a verb to say what the request is or what you want to do with it. Like, for example, you have get, but there are other interesting ones as well, like post, put, delete, head, connect, and so on. The second thing over here is the resource that you're targeting. Like in this particular case, it's just this slash. And then you also have the version string over here. And the second portion of the request is a set of headers. Like in this case, there's a host header that is a comma separated. So there's a comma to demarcate between the key and the value over here. The colon, sorry. There's a colon to separate the key and the value here. And then content length over here is a special header. And what it does is that you say how many bytes are going to follow. Like, for example, there's also the content length is going to say how many bytes are going to be there in the body, and moose over here is just a random header that, so you can also have like these specialized headers that the server is going to do nothing about. Like the client can put anything in there in terms of headers. Yep.
I made a mistake in making this slide. This moose line should be before that CRL left there. So I'm actually just going to edit the slide live. There we go.
Yeah, and then comes the body, which over here is 16 bytes, and that's why the content length over there is 16. And this is a TCP-based protocol, and we are primarily only looking at HTTP 1.1. And what you see over here is a sample HTTP response, where in the status line over here, you have the version string that's usually copied over. So there were several servers that we saw where instead of 1.1, if you just wrote 0.1, it would still put it back in here in the response body, in the response status line. And then you see a three-digit number over there, which says what the status code is. 200 is OK. There are 2 others that would be featured in the talk. There's the 403, which is either forbidden or access denied. And then there's also 400, which is a bad request. In that case, there's a parsing failure that the server said, no, this packet is bad, we're not going to process it. And over here, you also see that there's, again, a content length header. And in this case, it says 21. And then clearly, we've lived in New Hampshire for a while, so that's why it says live, freeze, and die. The carriage return line feed over here is CRLF, that's a delimiter, and that's used widely in the HTTP protocol. So I told you that these are verbs, and these are different request methods. So then there's a GET request, in which case you just ask for a resource. And in the GET request, having a content length and a body doesn't really mean much in the protocol itself. And then you can also have a POST request where you send some data to the server. This could be forms, This could just be some sort of JSON data that you're trying to send to the server. Then you can also delete resources, and that's the delete method in the HTTP 1.1 protocol.
All right, so HTTP is conducted over TCP, and it would be wasteful to open a new TCP connection for every request response pair. So instead, connections are reused in HTTP 1.1. So there's two different ways you can reuse a connection. The first we're calling ping-ponging, which is where the client sends a request to the server, and then the server sends a response to the client, and then just on the same connection, the client sends another request and receives another response, and they can go back and forth until one or the other closes the connection. The other way of reusing connections is pipelining. So that's when the client sends multiple requests just concatenated together right in a row on the connection to the server, and the server then responds with the appropriate number of responses. Okay, so that's the end of the whole background section. Now we can get into some of the vulnerabilities we found. This is like one of the first things we noticed is in this little web server called Sysanta Mongoose. So this is primarily used in embedded systems. It's written in C. There's about 10,000 of them if you search on Shodan right now, just facing the internet, but many, many more on internal networks. This is just when we were first getting started. So we were just basically setting up a bunch of servers, starting up an example application, and then just typing in requests and seeing what happened. So I'm going to show you what we noticed when we just started doing that. So let me pull up the demo here. Okay, and then great. So we'll start by sending a really straightforward request. I can make this bigger if that's a little less visible. Can you guys see that in the back? Yeah. Cool, great. Okay, so we'll send a really straightforward request to Mongoose. So here the request is just like a GET request with no headers and no body. And it responds 200 OK, gives us some HTML. Great. So what if we add a message body to this length, or to this message? Then GET requests with message bodies are not, the semantics of that isn't defined in the standard, but it is allowed. So I'm just going to type in 10 bytes and see what happens. And the server still responds with HTML. It seems like it just ignored the message body. I'm sorry? Yeah. There's also a server log down here that just says what kinds of requests the server received. So you can see it just sees another get slash, not different from the first. OK, now what if we put a minus sign here? Then this is not allowed in the protocol. This should be invalid, and most servers will give you a 400 when you put a minus sign here. But when you do this, Mongoose does something weird. So it responds with the same HTML, and then after, it tells you 404. And then in the log, you have h:-10 as the request line. And so that really looks a lot like this. And if you count out the number of bytes from h:-10, carriage return line feed, carriage return line feed, that's 10 bytes. So what if we change this to 11? Presumably, we'll get th:-11. And sure enough, yeah, that's what we get. So then, what if we figure out how long this whole thing is? And then see what's going on when we do that. So that's 39 bytes long. And it's a good thing that 39 is the same number of digits as 11, because we can just plug it in. And if we do this, then that happens. So the server's just stuck over and over parsing the same request, and it didn't respond either. So that's sort of funny. If we now try to send a legitimate request again, so we just change this back to a 10, it still doesn't respond. So the whole thing is just locked up in an infinite busy loop. Yeah, so this is, I thought this is really funny. So we can shut this down. We reported this. It's now fixed. So that's good. But because this is an embedded web server, If you look on Shodan, the vast majority of the instances of this server out on the internet remain unpatched because they live on weird little systems in people's closets, and no one's really thinking about them. So this most likely will still work on a given instance of the server. So why did this work? As we saw earlier, Mongoose supports pipelining. How best to handle pipelining? Well, pointer plus offset, pointer to the end of the header block, plus the content length. And if the content length is negative, then the whole thing falls apart. Great. Second vulnerability we're going to cover. This is in a web server called Lightspeed. Now, Lightspeed is actually the third or fourth most popular web server on the internet by number of sites hosted, which may come as a surprise to many of you. Certainly was a surprise to me because I had never heard of it. And the reason for this is that 99% of those websites are like small business WordPress sites. So no one, they just kind of don't matter so much. Yeah, so they market themselves as the fastest WordPress stack. There's a few 100,000 of them in the US and many more outside the US. And I'll just show you what we found when we were playing around with Lightspeed in a very similar way to how we were playing around with Mongoose. Okay, so here, if we start by just sending a request to Lightspeed, so we'll send HTTP 1.1 into Lightspeed on port 8088. That's where the example server runs. We send this, get a bunch of HTTP or HTML, and it's too much HTML, so we're just going to pipe it into grep, and we get a 200 OK. So that's a really basic request. If we add another request to this as a pipeline, then we just get two 200 OKs, so that makes sense too. And if we add a message body to the first one, then that actually is because I didn't type out 10 bytes here. So that was my mistake. If we add a message body, we still get two 200 OKs. So that all looks fine. And we were just playing around with this, and we said, what if we put a 0 right there? That should do nothing, right? It's just a leading 0 on a number. But if you put a 0 there, so just recall, no 0, two 200s. With a 0, we get a 200 and a 400. So that's kind of weird. 400 means you have a malformed request. And it's actually the second request that it thinks is malformed, but the content length header here is in the first request in the pipeline. So that's kind of confusing. We went into the code and just kind of looked at how they were parsing content length, and this is what we saw. So stir to LL, if you look at the man page, this is just a libc function. It's an integer parser. It takes 3 arguments, the string you want to parse, and then an unused argument they don't use, and then a base. So 10 would be decimal, 2 would be binary, and they put 0. So a base 0 number is not a thing. Does anyone know what happens when you put a 0 here? Has anyone seen this before?
Yeah.
I'm sorry? That's pretty close. I'm sorry?
It sniffs the base for you.
Yeah, it tries to guess. Yes. From the man page, essentially when you put a 0, it's going to look at the string, and if it starts with 0x, then the string will be interpreted as base 16. If it starts with 0, then it's interpreted in base 8. And if it starts with any other digit, then it's interpreted in base 10. OK, so this is the way that Lightspeed parses the 2-message pipeline without the 0. So it'll just see 2 requests with a 10-byte message body in the first. When you add the 0, you have an 8-byte message body in the first. And then the method of the second request is going to be 89get, which of course is not a real HTTP message or method, so it 400s. And that's why we have the malformed, why it's interpreted as malformed. So you might be wondering why any of this matters, right? This just seems to be some stupid bug in Lightspeed. But it's kind of just a bug that allows a client to invalidate a response intended for the client. So it seems like really no harm done, just a dumb mistake. OK, so we're going to introduce a new concept, and this is HTTP proxies. So it would actually just be a dumb mistake if the browser were talking directly to Lightspeed. But that's relatively less common than having intermediary servers that sit between the browser and the endpoint web server. So this could be a CDN, it could be a caching proxy, it could be just a reverse proxy that's doing load balancing, it could be enforcing access controls on the requests, the incoming requests. So the flow that we're going to see when we introduce a proxy into the mix is going to look more like this. So Firefox is going to send a request to HA proxy, which is just a web proxy, can do caching, can do access controls. And HA proxy is going to forward that request onto Lightspeed, totally unchanged. Lightspeed is going to turn around and respond to HA proxy, and then HA proxy is going to take that response, again unchanged, and just send it right back to Firefox. So that's generally the mode in which HA proxy works. Now, we're going to essentially consider proxies and CDNs and caches as all being elements of the same set. They're all just HTTP transducers. They take in requests, potentially rewrite them or normalize them or modify them a little bit. In the case of HA proxy, that doesn't happen, but that can happen. And then they forward them on to some other server. That's kind of the framework we're working under. For our purposes, CDNs are not really too distinct from just a normal load balancer. Okay, so let's start up another demo. And this time we're going to add HA proxy into the mix. So we have an instance of HA proxy that is pointing at Lightspeed, just as shown in the graphic a minute ago. So if I send a request to HA proxy, then when I get a response, it's a bunch of HTML, and if I just look at where that response came from, you can see there's a server header set to Lightspeed. So this is just saying the response came from Lightspeed, indicating that HA proxy is working as intended. Okay, so HA proxy presumably does not have this mistake with the weird octal content length parsing thing. So maybe we can exploit this difference. So I've configured an access control list in HA proxy. So if I ask for /.ssh/ID/RSA in HA proxy, then HA proxy will say 403, you can't do that. And that's because I just added some option in the config file to deny requests that look like this. And if we want to get around this access control list, then maybe we can take advantage of that parsing discrepancy between HA proxy and Lightspeed. So here's a big, ugly payload that I'm going to copy and then try to explain. Okay, so we start with a GET request for /, and we have a content length set on that GET request of 0-200. Then we have, from HA proxy's perspective, we just have 200 bytes after that. So this highlighted region is 200 bytes. So HA proxy will see this payload as one request with a 200-byte message body. Now Lightspeed is going to see the same payload as, it's going to start out the same, right? It sees get / the content length of 0-200, which in octal is equal to 128 in decimal. So it's going to see 128 A's right here. This is 128 A's. And that's going to be the request's message body. And then there's going to be another request after that. So from Lightspeed's perspective, there's 2 requests in this payload. And the second request, well, that's asking for ID/RSA. So if all goes according to plan, we should be able to send this to HA proxy. HA proxy will forward it to Lightspeed. Lightspeed will respond twice, once for / and once for ID/RSA. And then we should get those responses, and we'll have done our job of bypassing the access control list. Except it seems like we just got HTML. So let's look at what the responses look like. And actually, there's only one response. So something strange is going on. We send this, but we only get one response. All right. So maybe this is what's going on. We're sending requests with Netcat. We send our payload to HA proxy, and HA proxy sees one request. HA proxy forwards that to Lightspeed, which sees 2 requests. Maybe Lightspeed actually does respond twice with the private key. But then HA proxy is only expecting one response, so it's just going to say, oh, something strange has happened, I'll just drop that second response on the ground and forward only the first. So perhaps that's what's going on. And if that were going on, then the solution would just be to make sure that HA proxy and Lightspeed agree about the number of requests sent, but maintain the disagreement about what those requests actually say. So we'll go back to the demo, and I'll just restart these containers and try doing this again. This time, I'll try adding another request to the pipeline. So this is the same payload as before, and I'm just going to add yet another GET request onto the end of it. And I'm going to set a host header here. And I'll explain the reasoning for that in a minute. So if I add another request to the pipeline, then HA proxy will see 2 requests, and Lightspeed will see 3. But we can fix that by changing the content length value of the second request that Lightspeed will see. So the length of this we can grab. So the length of the new request we just added is 33. We can add that to this, 23, to get 56, and send that into HA proxy. And there's our private key. All right. So I set that host header earlier. And the reason I did that is that HA proxy also can act as a cache. And that cache is only going to work when a host header is set. So now we can take this even a step further. Given that HA proxy's interpretation of this whole thing is that this request was sent and a private key was received in response. So it must be that when you send this request, you get that private key. And so it's going to put that in the cache. And if we just wget HA proxy, and we look at this file we just got right here, we also have the private key. OK. And then also, we have our demos on GitHub, and we got an email saying we shouldn't put private keys in a GitHub repo. I think this is an exception to the rule.
So what you saw here, were two examples of what can happen if you do misinterpret how the HTTP requests are handled. So when you have a front-end server and a back-end server and they disagree on how to parse the HTTP requests, the side effect of that is pretty much request smuggling. And bypassing ACLs and cache poisoning are just like 2 side effects of this happening. And to just explain what just happened, what you see here on the left is the interpretation that HA proxy has, where it sees that it's a 200-byte message body, whereas Lightspeed sees it as 128 bytes because it interprets 0 to 100 as octal. So then you see 3 request lines over here, 3 lines with the get request method. And you see that HA proxy sees the first and the third, whereas Lightspeed only sees the first and the second. And so then essentially both are seeing 2 requests, but then which 2 requests is the point over here. So you might think that these are pretty obvious mistakes. And HTTP seems pretty straightforward. So why just parse the content length, right? I mean, it's just an integer. Just get it right, a positive integer without the positive sign or any signs. But then you can just pretty much parse this number and you just get it right, right? Not really. I mean, when you actually look at the spec, there are essentially 8 rules on how you need to handle message bodies. But then when you start diving deep into it, you see that this first one is about the head request and not about get or post. So I guess this is not relevant for this one. And then we see the second one, which is again about the connect request. I guess, again, that's not relevant to this one. This one is relevant, though. But then it says, it's again an exception. It says that when you have this other special header called the transfer encoding, when that's present along with content length, then what do you do? And then there's this one, which says what to do when the transfer encoding takes a specific value. And then you have this one, which says that when you have no transfer encoding, but the content length is invalid, then what do you do? And have I confused you all enough? And then you also have like the valid content length header without the transfer encoding. This is what we are probably interested in. But then you have these two messages which are like, when you have the request message and none of the above are true, then what do you do? They just say that there should be no body. And then they say that when you have a response message without the declared body length, then you should parse everything all the way to the end of the server connection closing, and all that is the body. So that's how complicated this is. And then if you thought that was enough, then there's a whole blob of text that says there are exceptions to all the rules I just mentioned. So yeah, I mentioned that there's another special way that you can, a special header for you to handle the message body, and that's called transfer encoding chunked, which is essentially used when streaming when you don't know how large the body is going to be, and you cannot specify what the content length is, and you want to send the response in chunks. So then you just specify this, and then you say that the first line over here is the chunk length, which says A, which is interpreted in hex, and that's why you have 10 bytes, followed by the CRLF character. So then you can also have a 1A over here, which is 26 bytes, and that's why you have the body A through Z. And then you have an empty chunk length over here, and that's how you terminate your chunks.
Right. So then there's a little used and little known part of the grammar called chunk extensions, and this is where you add some amount of white space optionally, and then a semicolon, and then a key value pair separated with an equal sign, and the key is going to be, it can be quoted, but it doesn't have to be quoted. And then you can put more key value pairs, and you separate them with commas. But you can actually put commas in the quoted strings, so you can't parse this by just doing split on commas. So this is the level of forethought that went into these standards. Anyway, it turns out no one uses this, so it doesn't even matter. A lot of servers will just ignore them, and many of them don't even make it accessible through the scripting backend. I think the original intent was for checksumming the chunks, but this is all over TCP, so it's reasonably reliable, and that doesn't really come up too much. Many transducers will actually just take those chunk extensions and just rip them out before forwarding the request, because they just cause too much annoyance. Also, this optional whitespace here before the first chunk extension, that's not just regular optional whitespace, that's called BWS in the standard, which stands for bad whitespace. And bad whitespace is whitespace that you should accept, but you must not produce. So if you receive a request that contains that whitespace, you should allow it. You should never send any requests that contain whitespace there. And that means that a proxy or a transducer needs to normalize out that whitespace if they're conforming to the standard.
I think there is the keywords over here being should and must. I think like should is supposed to be permissive, like you should really do it, but it's really okay if you don't do it. But then must is a lot more strong, and if you're familiar with standards, I think there is a hierarchy to these keywords here.
Yeah, that has its own standard. Okay. So the next natural question is what counts as white space? And so RFC 9112 defines BWS to be go look at RFC 9110. And then RFC 9110 says BWS is equal to OWS. And that stands for optional whitespace. And so then OWS is defined to be any number of spaces or tabs. Okay, so that's it. Except then RFC 9112 says there are some contexts in which a space is what you should accept, but you can also optionally choose to accept tabs or vertical tabs or form feed or carriage return on its own. And then there's also, so it seems like, right, carriage return on its own should be allowed in that context. But then it also says you must not produce carriage returns on their own, except inside the message body, where, of course, arbitrary binary payloads are allowed. And then if you receive a carriage return on its own, so i.e. not followed by a line feed, then you either have to consider the whole thing invalid and just reject the message, or translate it back into a space. So even just the question of like what is white space is not very clear. If you just read the grammar, you get 1/3 of the picture. So this is from this, you can probably guess that implementations are pretty inconsistent about this. So here's a list of transducers that will forward carriage returns within the bad white space before a chunk extension. So Google Cloud's load balancer will do it. Akamai will do it. And also Apache Traffic Server will do it. Google and Akamai have now fixed this. So Akamai now 400s when you try to stick them in their carriage returns in that white space. And Google will just strip out all the chunk extensions now. So this isn't a problem anymore there. Apache Traffic Server hasn't fixed this. We reported it a really long time ago privately, and they said, that sounds like a problem. And then nothing happened. So then we reported it publicly, and still nothing has happened. So it turns out there's also one pretty popular endpoint HTTP parser that interprets carriage return followed by anything as equivalent to carriage return line feed in this particular context. And that's Node.js. So if you have Node.js on Google Cloud with a load balancer in front of it, or if you have a node-based service with Akamai as your CDN, or if you're using Apache Traffic Server in front of Node, then maybe there's something interesting we can do with that difference. Okay, Node also, by the way, fixed this bug, but only in a feature release. So if you get Node from the Debian bookworm repositories right now, you actually get the vulnerable, or the version that has this bug.
Same for ATS.
And same for ATS. So when we do a demo in a second, that's just using that's just apt install Node and apt install traffic server. Anyway, so yeah, it seems like most HTTP implementations don't really get the spec 100% right, mostly because it's really complicated, and also because the standard is just, it comes from a time where permissiveness and flexibility was considered really important for a network protocol, and that's just, I think we can probably all agree that's just a bad idea in hindsight, but we need to maintain backwards compatibility. Okay, so another demo. This time, I'm going to start up Node and ATS, Apache Traffic Server, and then my little attacker container. All right. So I'm going to start by sending a request at Apache Traffic Server. So Apache Traffic Server is pointing at Node. So this is very similar to the HA proxy Lightspeed configuration we had earlier. We just have Apache Traffic Server. When you send it a request, it's going to forward that request over to Node, and then Node is going to respond, and that's it. So I have a very simple application in JavaScript. It just responds to every request with served up by Node.js, unless that request is a delete request, in which case it will say something different. But we've actually configured an access control list on Apache Traffic Server. So if we try to delete slash, we get 403. So yeah, Apache Traffic Server will block all delete requests with this configuration. And so here's a payload that will actually get a delete request through Apache Traffic Server. So here you can see we're doing a bunch of stuff. I'll explain that in a minute. But we're going to be piping it all into netcat to ATS. So when we do that, we get this response here. So we did get a delete slash through the load balancer. And in fact, this exact attack used to work on Google Cloud's load balancer and also used to work on Akamai for the same reason. Okay. So how did this work? Yeah, so here's Node's interpretation of the payload. So it sees two requests, a post and a delete. And the post has, so here where we have yellow, that's length fields. And where we have purple, that's data. So the post has a chunked message body, with the first chunk being 2 bytes long. And that length there is delimited with carriage return. And recall that Node will accept carriage return anything as the delimiter here. And then we have some data, and then another chunk, and data, end of chunks, and then a delete. And then Apache Traffic Server is going to see that same data, and it's going to see that those carriage returns here as being part of the optional white space before a chunk extension. So it's actually going to ignore this semicolon A as being a chunk extension. And so the 0.2 is going to be a length, and the 2D is data. And then so you can see the roles have flipped here. What is data to node is length to Apache Traffic Server, and what is data to Apache Traffic Server is length to node. And then we have a big, long blob of data that happens to contain a delete request, but is just opaque data that we can ignore. And then we have a 0-length chunk, and then a totally benign GET request. So that's ATS's interpretation, and that explains why it would let this payload through. Except you may have noticed that there's a content length on this delete request, and it's 183. And that's way longer than this message body here. So the reason for that is that Apache Traffic Server, when it receives a request, it just kind of crams it full of some extra headers. So it puts in some information about what the originating IP is, and it also just puts a really long version string into the request. So you need to take this into account when you're smuggling. So you need to basically pad out this content length to take into account the fact that this GET request right here in the message body is going to get made way, way longer. And so that's why we have the weird-looking content length. This used to work on Google Cloud. You could poison cache, and you could bypass what's called Google Cloud Armor policies. And they gave us a $6,000 bounty for figuring that out. Yeah. This also worked against Akamai to bypass their equivalent structures and poison that cache, but they don't have a bug bounty program for their CDN, which I think is their biggest product. But that's changing. That is changing. I have an email from a colleague at Akamai who said they're starting a program, and this is maybe a month or two ago, and that we're on the list for when they do start the program, but I don't know when that will be. Yeah, so this was the impact here. Okay, I'm going to pass it back off to Prashant.
Cool. So how did we actually find all these things, right? So the core idea over here is that we have something called the HTTP garden, where we have configured most of the servers that you would find in the wild, and most of the transducers that you would also use in the wild. And everything over here revolves around the driver script that sends these HTTP requests to the set of all transducers that we have configured. And the transducers then forward these requests to an echo server that we have set up. And the echo server essentially just grabs whatever it got as a request and puts that in the HTTP response body and sets the right content length and sends it back to you. So then the transducers then pass it on back to the driver script as well. And then the driver script, what it can do is that it can grab the payload from the transducers and then pass it on to all of these servers that we have configured. And then the servers are configured to respond back in a JSON format that we have, where it responds with the exact headers that it read, as well as the request URI, the target, the request method, and also the version string, right? And then, and the other thing that we have also done is that we are doing something called differential fuzzing, where we have an input generator that takes into account coverage as well as a grammar for HTTP 1.1, and then it keeps passing on new input to the driver script based on previous coverage information that we've gathered. And the entirety of the HTTP garden relies on two core tenets. The first one being that the servers do convey their interpretation of an HTTP request, and they do this with the help of their scripting backend. For those of you who are familiar with PHP, you would recognize what's on the right here, which is how PHP actually, you can grab what the request method, the URI, the version, all of those things, how you can grab them. The one thing missing in this particular code snippet is the headers not being extracted, but we had a separate method for that.
And the message body.
And the message body is right here.
Yeah, you're right. Never mind.
Yeah. The other core tenet over here is the effect of the transducer, and we observe that by pointing it to an echo server. And we configured a bunch of them. I'm just going to leave it here for a second for you guys to see, but there's plenty of them, and you would recognize most of the popular HTTP servers. We've configured them, and they all respond with almost the same JSON output. And similarly for the load balancers, all of them, they point to the same echo server that we have. Yeah.
So it's worth noting, we found at least spec violations and sort of harmless bugs in the vast majority of these programs, and more serious vulnerabilities in a lot of them. We're kind of restricted on time during the talk, but if you want to come up to us after, we have loads and loads of these bugs we could talk about. So especially weirdly, the OpenBSD HTTP stack, which you think of as being like kind of designed for security, has a lot of these sorts of problems, which kind of gets at this deeper insight, which is that traditional secure programming practices for like systems programmers really don't carry over so well into this domain.
Yeah, and you'll also notice that there are some external services over here, like the Microsoft IIS server. We didn't want to, most of our things rely on Docker, and we didn't want to mess with that beast. To conclude, that brings us to the end of our talk. Never rely on the assumption that two parsers for the same format agree. If you really have to rewrite your parsers, make sure to fuzz them while comparing them to the other implementations. And if you want to use access control policies, don't just trust that the CDN or the HTTP proxy that you have configured is really going to work. And I think the last one here is a bit cheeky from Ben, but yeah. Cool. Fastly actually gave Ben a hat, and that's what he's wearing. It says Security Hero. They also gave him a coin. And we got a total of 11,000 in bounties from Google. We only talked about one of them. There's another one which is not as cool, but still interesting. And that brings us to the end, and we'd be happy to take a few questions from you all. I think we have about 7 more minutes. There's a mic here, sorry. Yeah.
Out in the wild, how easy is it to take advantage of this? I mean, like if you think of things like SE Linux or something that's keeping that web server from accessing, say, SSH or something like that, is this actually common out in the wild? Is everybody just running? Did you get to test any of that or see any of that?
I can take that. So out in the wild, it's sort of difficult to just kind of figure out even what the server chain looks like. So we didn't spend a ton of time trying to exploit real systems because it's kind of just, it requires specific work digging into the weeds on like how does PayPal implement this particular service. And that's kind of just not so interesting to me. But in short, SE Linux or like configuring policies about what a certain program is allowed to access does mitigate like path traversal, but if you're trying to protect resources that are within the server root, then none of this will matter. So that's a partial mitigation, but my expectation is that in many real-world scenarios, SE Linux is not sufficient to prevent this sort of attack.
Yeah, I think the whole reason that this works is because there is a chain of servers or a chain of HTTP parsers. And that doesn't, like having SE Linux policies is not going to prevent this from happening. And when you have such mismatches between the parsers, ACL bypasses and cache poisoning, even desync, we couldn't demonstrate it because it's not very reliable to show in a talk, but even desync is quite possible.
Yep. Quickly, I should just define what desync is. That's just when you send a request and then you get a response intended for someone else. So that is something that was possible with a lot of these bugs, but it's really hard to pull off. It's pretty inconsistent. Portswigger had some interesting stuff about doing this using HTTP2. And so if you're interested in that, I recommend checking those out.
Yeah, please.
Hi there. Great talk. Wow, loved it. I'm asking this just in case anyone else in the audience is interested as well. If, let's say, there's a SaaS that has a tool chain, maybe sees themselves as a bit of a CDN, are you done working on this? Are you interested in being invited to go do some poking where you might find something and submit through a bug bounty?
I'm sorry, could you speak up for the last part?
Are you interested in getting directed to a bug bounty program to go repeat some of your work?
Absolutely. I think, yeah, I mean, we've mostly reported most of the things that we have found, but we've also not run our differential fuzzer for a large amount of time reliably yet. So I'm pretty sure we'll find more as we keep improving on our grammar and getting more and more coverage. So absolutely, yes.
Yes.
Did you explore any HTTP2 downgrade issues back to 1.0 or 1.1?
Yes, we completely saw this question coming. So we did, H2O being one of them. There was one more server having issues with the
Envoy, yeah.
Varnish, Envoy, H2O. Those three absolutely had issues, but we really focused on HTTP 1.1. I mean, you need to keep state when you try to explore HTTP 2 and 3 also. So, and the other thing over here was also that it still accounts for a majority of the HTTP traffic that we saw. Because although the front-end server could talk HTTP 2, the things on the back end, it almost always gets rewritten.
We did see some interesting stuff with downgrading, in particular in H2O, which is a Fastly's load balancer. They have a really funny thing, which is that when they downgrade from H2 to H1, that HTTP 1 isn't necessarily HTTP 1 that they would have accepted had you sent it to the server originally. So this is kind of an interesting vector. So there are slight differences in terms of what constructs are allowed in H2 versus H1. For example, HTTP 2 allows empty header names, and HTTP 1 doesn't. So if you downgrade from an HTTP 2 message that has an empty header name to an HTTP 1 message, H2O used to allow that empty header name. It would forward an HTTP 1 message with an empty header name, which would then get rejected by the next server in the chain. We saw some other weird things like that, but we didn't look too deeply beyond that sort of thing. We were finding other problems with white space handling and how that differs between H2 and H1, but nothing of particular note.
I think we have time for one more question if anyone has any. Cool, thank you all. Thanks for coming.